Okay, so we learned a very abstract definition of work, and I agree it's very abstract. That's why I think it's a bad point to start to think about energy, and hopefully the way we started with last lecture about understanding energy gives you a better intuition of it. But yeah, we have to deal with this, so we're dealing with it. And it has its use. For example, I've quoted these formulas, these three in particular, the energy of the gravitational potential energy of the Earth, the gravitational potential energy of the universal gravitation that is stored between the gravitational field between two objects, and also the stored energy in a spring. Well, it follows these formulas. All right. So how are we going to find out? So how do we know where these formulas come from? Like, how do we know to use these formulas? And it's really from the definition of work. So gravitational potential energy, I haven't really defined it properly. I told you intuitively, it's the energy of height. We're specifically talking about on Earth. I told you if something has a given height, it has energy, and it's given by that formula. I haven't shown you why. But now we can do it because it's defined as the work done on an object by gravity. Okay, so you see it's on an object by a force, always the same case. All right, so what is, let's see what happens, right? What does gravity do? Gravity moves objects down on Earth. We'll focus on Earth first. Now move objects towards the ground. All right, let's get our axis right and try to do the calculation, right? So let's use the standard XY axis. I'll set this as y equals 0, y equals to some heights like this, okay? And let's use our definition. Now, what's the force during this whole process? At every single point of the box falling, the F, the force of gravity on it is mg, right? But that's the magnitude. How about I need the force vector, and does it go in the x direction? No, not with my axis, but it's mg in the downwards direction, right? You see, if you draw a free body diagram, it's pointing downwards. So if I define y that way, I'd better put a minus sign, that's fine. Okay, and what is my displacement? My displacement, it goes from here to here, so nothing in the x direction, but y is minus h, right? It's going final minus initial, so that's it. Now, is f a constant or not? It is a constant. And is it parallel to my displacement, right? My displacement is this way. Yes, f is parallel to the displacement. So gravity is indeed doing the work over here. So I can use the simplest of those formulas. I can use the complicated one, but I'll just go ahead and use the simple one, right? It's just the force of gravity times the magnitude of that. So I just need the magnitude of this times the magnitude of this. What's the magnitude? It's mg. And the magnitude of this is h. And there you go. So that's the amount of energy gravity has used to move it from here to here. Okay, so so now you can reverse the logic and say, how much energy do I need to move it up a given height? Well, if gravity took mgh to move it down, you will need mgh to move it up, that amount of energy. So that's the reason why we use, if something is at a given height, you've basically overcome the gravity by that much joules, that much energy. Okay, so I much rather, hopefully this is intuitive, right? So now you know where that comes from. Hopefully this is much more intuitive to use energy to understand work than using work to understand energy, which is the usual textbook ways of doing things. Okay, let's see, what can I say about this? Yeah, if you want, you can use a more complicated version of it as well. For example, let's not use the most complicated, but the second most complicated, just with the dot product, right? So you go like, hey, let me try the dot product version of it because I've just learned it, might as well try my hands on it. So you have 0 minus mg dot 0 minus h. What do you get? Well, 0 times 0 is 0 plus minus mg times minus h. What do you get? mgh. So you see, even if you want to use the more sophisticated version, you will get the same answer. You can use the integral as well, which is drastically overkill, but sure. Initial to final force dot dr, right? So you will have, there's a couple of ways you can do it. You can pull this out, but that simplifies a bit. But you can leave that in as well if you want. What is dr? Dr is, so let's put an F first, I know that, mg, right? So dr is the path going from here to here, but it's a small change in path. So so dr in terms of a vector is dx dy, like that. If that confuses you, write it in component form. That's what it means. Okay, so it means a small distance, in a small change in position, a small displacement is a small displacement in the x direction and a small displacement in the y direction. Okay, so whenever you have dr, that's sort of the general form of it. In this case, I can actually plug in dx equals to 0 and just work with dr or dy. But either way, it doesn't matter, because as you can see, if I put it here, 0 times this is going to be 0 anyway. But if you like, you can just say, hey, I know in advance my r is just my dr, it's not moving in the x direction. I can plug in 0 for that immediately. Okay, but either way, as you can see, it becomes 0 times that. So 0 plus minus mg times dy. Okay, but mg is a constant, so you can pull that out. So minus mg, integrate initial to final dy. What's integrate dy? That's y, but I need to put in initial and final. See if I can squeeze that in some way here. So we have minus mg, y final minus y initial, mg. What's y final? Y final is 0. What's y initial? Y initial is heights, so y initial is h. So I have minus mg times minus h, right? It's mgh. As you can see, drastically overkill, but it gives you the same thing. Okay, so now hopefully I've done it with 3 times, so you sort of get a feel of they're all the same. All right. Yeah, so now hopefully you understand exactly why it's mgh, and you see work done gives you a better better understanding of everything.